In this video, I'm going to talk about optical coherence tomography, or OCT. OCT is a technology that's used in medicine for imaging tissue in cross-section. Unlike other imaging technologies in medicine, OCT is restricted to more superficial layers of tissue, so we can't see deep into the body. And because of that, we use it in fields like ophthalmology, where we're looking at eyes, or dermatology, where we're looking at skin. Now, before I jump into it, I want to provide a brief example. This is a crudely drawn cross-section of the eye, and here we've zoomed in on a part of the eye, the back of the eye, known as the retina. And the retina is responsible for receiving incoming light, providing some pre-processing, and then shipping that information off to the brain. And as you can see, it's a deeply complex structure, so there's a lot of tissue layers involved in this process. And in a disease, any one of these layers can be affected. So being able to see the different layers of the retina is really important, and with OCT we're able to do that. These are both images taken from Wikipedia. In this image, we can see that using OCT we're able to discern different layers of the retina, so that if one layer were affected because of a disease, we would be able to see it and it would help with the diagnostic process. But what is OCT? To start, I'm going to look at the name here, so Optical Coherence Tomography. Optical just refers to light. So unlike ultrasound or some imaging that might use sound, OCT uses light. Coherence is a property of light, specifically light of a constant phase difference. So I'm going to write down constant phase difference. And this is sort of analogous to monochromatic light. So I'll write that down too. Monochromatic. Mono means one. Chromatic, color. Yikes. So one color of light, a single wavelength of light. And when you have monochromatic light, interference becomes available. So I'll put that in parentheses. Interference. And let me illustrate what I mean by this constant phase difference. So to do so, I'm going to just draw a couple of waves here. These are both going to be red light. So here, also going to have red light. And as you can see, with both of these red light, the wavelength remains the same. So the wavelength is this peak to peak distance. And regardless of where the peaks are, the wavelength is always the same if you have a single color of light. But these waves are not the same. You can see that they're a little bit different. This, you would imagine, might look the same as this if we just shifted it over to the left. And so this horizontal difference in the peak position, this shift here, move this over to here, that is called the phase difference. Phase difference. When things are in phase, the peaks align with one another. So if this peak matched up with this peak, we would say it's in phase. When the peak matches up with the valley of the other wave, that's called out of phase. So I want to draw just a couple extreme examples. And interference is just the summation, the adding of light waves. So here's a situation where we have two light waves. I just drew them in different colors, but they have the same wavelength. Just wanted you to be able to see that there are two waves, and if we were to interfere these, well, the peaks match the peaks, the valleys match the valleys. So these waves are in phase, and so they would interfere constructively. So you would get this sort of extended shape here. I'm going to put down a couple words: in phase, constructive. How about if the peak of one wave matched the valley of the other wave? So peak matches the valley, like such. And in this case, if we were to add the waves, if we were to interfere the waves, we would just get a straight line. And this would be a dark, we wouldn't be able to observe anything. And this is out of phase. Out of phase. Of phase. This is destructive. Interference is only available when we have this monochromatic single wavelength light. If the peaks match the peaks in one spot, so say we have orange light where it's a slightly shorter wavelength, peaks match the peaks, but it's not a constant phase difference. This is not constant, so we don't get coherence, and so we can't call that coherent light. Finally, what is tomography? Tomography is just imaging by sections. I'm going to put down slices, and this is just as we saw before. We had one cross-sectional view. We can use this imaging technology to get multiple slices and then reconstruct the tissue. So if we have a specific structure we're interested in, it might change a little bit from slice to slice, but we can see the structure in 3D using this technique of tomography. So the full title, Optical Coherence Tomography, really just means to image tissue by slices using this coherent property of light. So to illustrate the science a little bit better of how we're using this coherent light, I am going to first move down here, give ourselves some space, and then I'm going to refer to a classic physics apparatus called the Mickelson Interferometer. Mickelson Interferometer. And in the Mickelson Interferometer, we have a monochromatic coherent source of light, laser. And the laser is emitting a beam of light, propagates over towards the right here, and then is incident upon a sort of half mirror. So I'm going to draw this as a dotted line. It's a half mirror. And what happens is half of the light is reflected upwards. And then actually, what I'm going to do here is trace this out so that we can split the light up. So this is the same beam of light, but it's just making this a little bit easier. Half of the light is then propagated straight through this half mirror and follows off to the right. And this light is incident upon another mirror, and the light that travels upward strikes another mirror and is then reflected back downwards, and as it travels back down, it passes straight through this half mirror and proceeds downwards. And then the light that came over to the right here also strikes the mirror, passes back, but this time hits the half mirror and is reflected downwards. So we have these two beams that traveled the respective legs of the apparatus and then are recombined, and then finally they strike a detector, and I'm just going to draw an eyeball down here. So this is how we're seeing what happens. So I want to define a couple of lengths here. that make this a little bit easier to understand. The first is this length, the length of the sort of upward leg of the apparatus. And I'm going to call this L1 over 2. And this rightward leg I'm going to call L2 over 2. And the reason I'm calling it over 2 is because really it's traveling this distance twice. It has to go up and back, and so in the full round the path journey, it's going a full L1, and this is really a full L2. And so I want to define a couple of cases here. Case 1 is that L1 equals L2. That is, the light that travels up is traveling the same distance as the light that travels off to the side. And remember, when it hits this half mirror, everything is in phase. The peaks match the peaks, the valleys match the valleys. It's the same light. So this half mirror is splitting the light, and when it starts in phase, that means that if it travels the same distance, it stays in phase. So if it goes up, down, up, down, up, down, and it goes up, down, up, down, up, down, and says that goes that 10,000 times. Well, if this one goes up, down, up, down, up, down 10,000 times, then when it gets back, they're both going to be on and up, and so the peaks will still match the peaks, the valleys still match the valleys, and we get this thing that we saw up above. Peaks match the peaks, valleys match the valleys, and remember this is constructive interference, so we just get this accentuated peak-valley structure, and this is going to be a bright spot. Let's talk about another case. What if instead of L1 equaling L2, L1 goes a little bit further than L2. It goes further by a distance of half a wavelength. So lambda over 2. In this case, remember they're still matching when they first hit the mirror, but this one is traveling a little bit further so that it's going an extra peak. So it goes peak, valley, peak, valley, peak, valley, and then it goes peak, and when it gets here, it's on a valley. Meanwhile, this goes peak, valley, peak, valley, peak, valley, and then when it gets here, it's on a peak. And so we have a peak matching a valley, and a valley matching a peak. And remember, this is a case from above called completely destructive interference, and we got a dark spot. Finally, case 3, we have L1 equals L2 plus a full wavelength. And in this case, remember it's going peak, valley, and it goes peak, and then it goes valley, and then they're back to in phase. So the peaks again match the peaks, and the valleys again match the valleys, and we again get a bright spot. So bright again, and as you can see, what happens is as we move this mirror here, as we change the length of L1, we can recover this bright, dark, bright, dark, bright, dark view of the interference. Now what happens if instead of a mirror right here we have some other structure, some sort of tissue or cell or some other reflective structure that light is being bounced off of? Does anything change? Well, the short answer is no. Everything remains the same. It doesn't matter what light is reflecting off of. The light doesn't care. It just cares that it's being reflective. So we can get this interference pattern regardless of what the light is being reflected off of. So you might say, okay, well maybe we can use this in our technology that we want to see tissue with. If this is tissue, then we can use this to see the interference pattern. That's good. That's a good start. But I want you to consider, what if we have a reflective structure down here and a reflective structure way out this way? What happens then? Can we get this interference? And the problem is that with this, we don't really know what is being interfered, what the light is bouncing off of. Some of the light might be bouncing off of this, and we might get an interference pattern from this. Some of it might be from the same distance as the mirror. Some of it might be from way out here. So we can't really tell localize where this reflection is occurring, and that's important if we want to recreate the structure of the tissue. So what can we do? I'm going to first erase these cases here. What can we do? Well, a quick solution that you might think of is that what if we just send a quick pulse of light out from the laser? What if instead of this constant stream, we just send a quick pulse, so that a pulse comes and a pulse hits the mirror and a pulse gets reflected upwards, and then a pulse continues through, straight through, and in this situation, if we have a structure way out to the right, then if the pulse continues through all the way out here and it reflects off of this, then the light that initially went up will have gotten to the detector way before the pulse from out here, and so we won't get an interference pattern. Conversely, if the pulse were to come over to the right and hit a structure that was really close to the mirror and got reflected back, then it would get to the detector way before the pulse that came up here. And so we have a pretty good solution, and this does work, it would work, does work, but the problem is this pulse needs to be ultra fast. So remember, how fast does this pulse need to be? Well, light travels at 3 times 10 to the 8th meters per second. So if we open up this laser for a pulse for an entire second, then that's going to let 3 times 10 to the 8th meters of light escape. That is more than 7 times around the world. So that's not really giving us any information about where this structure, this tissue, is localized. And so to get an adequate pulse, to get good resolution of where this structure is, we need a pulse that is about 10 to the minus 15 seconds. That is a femtosecond pulse. And that's really fast, and so that, as you can imagine, might be a little bit expensive. So there is another solution to this problem of localizing the tissue, and that is to use, again, remember, we're looking at monochromatic coherent light, so just red light in all of these examples. What if instead of monochromatic light, we include maybe just a little light that's not quite red? And I'm going to draw this as orange. That is an exaggeration. It's not orange, it's just a little bit off of red. So what if we include light that isn't perfectly red? So this is our first red light, and then this is orange. So remember, with orange light, the wavelength is a little bit shorter. Okay. And so if the light, if L1 equals L2, and they travel exactly the same path length, then the light in this situation, put down L1 equals L2, the peaks of the light match up pretty well. So the peak of orange and the peak of red match up. The valley of red and the valley of orange match up pretty well. But as we go further and further out, as L2 becomes increasingly longer or shorter than L1, the peaks and valleys don't match up very well, and we get really just a jumble of interference. And really there's not interference here. I mean, we can't discern exactly what's going on. So this allows us to see interference only when L1 is approximately equal to L2. And the distance, there's a name for this distance here. This is just, again, a sort of a crudely drawn interference pattern, but this is called the coherence length. This is the distance where we can still recover some interference information. Beyond that, it's all just a jumble of stuff, but in this distance, the light will still interfere with itself. And so we call that the coherence length. And the coherence length is proportional to the wavelength of light squared over this number. And this is called the bandwidth. I'm going to write down bandwidth. And as we have a wider bandwidth, that is just saying we have more and more orange light, or we have a larger spectrum of light. So let's just look at some extreme examples. What if we have just perfectly red light? That means that the bandwidth is going to be very small, and this coherence length, the length where light can interfere, will be very large. So we saw that in the interferometer initial experiment. But what if we have a lot of orange light? What if we have white light with the full Roy-G-Biv spectrum? Well, with white light, this distance is going to be very small, and so we really don't have any coherence, and that's why we call it non-coherent light. But if we have sort of a medium, then we can recover interference for a short distance, and that is what we call the coherence length, and that is really what the resolution of OCT is, the coherence length of the light. So how are we using this? Well, let us just look at an example where we have maybe a few layers of tissue. We have a nice blue layer there, and greener layer, and maybe a pink layer. And so what we do is we can adjust the mirror of the L1 leg of the apparatus so that the L1 is equal to L2 for the blue layer. So we want to see L2 for the blue layer. We make this the same distance, and then we send in the light, the broad bandwidth light, and we see the reflection, the interference pattern for the blue layer. And then we adjust the distance of the mirror for L1 so that it equals the distance for the green layer. So L1 equals L2 for the green layer, and do the same thing for the pink layer. And as we go, we're building up a reflection pattern of all of these layers. So we're looking at the reflection pattern of each of these layers, and then we can move it over and do the same thing over here and the same thing over here, and eventually we have a full cross section that we saw in the beginning of the retina. So I hope this helps you understand a little bit about how OCT is working to determine a cross-sectional view of the tissue.